Thank you, everybody. It's always a challenge to follow Marcel because he's such an excellent rhodocologist and the way he thinks, and I really appreciate that last section there about how we think about roads and biodiversity in general. I'm going to talk, it's actually a good starting point. I'm going to talk about planning wildlife crossing locations. While I'm talking about wildlife crossings, I want you to keep fencing in the back of your mind as well. And this is work that's taking place at the Road Ecology Center and at Dudek, a consulting firm in California, and mostly in California. And my co-author is Clara Woody. I want to acknowledge, want to acknowledge the Wildlife Conservation Board. The Wildlife Conservation Board a couple of years ago received $200 million to help with wildlife crossing planning in California, and has received another 100 and something million, I keep forgetting, under Prop 4. And I think this puts it at the same scale as the pilot wildlife crossing program at the federal level. All of this was relatively unexpected, and they've done a stellar job of suddenly being able to turn this money around into planning, and I'm going to talk about several of those. I want to thank Caltrans for a constant and wonderful partnership and collaboration, and a variety of different individuals and organizations that have contributed to what I'm going to talk about. Okay, so the problem that I'm going to talk about today is that we assume that wildlife crossings are going to solve connectivity issues, and we also have to irreversibly commit them to a certain location. So if we're really going to actually solve a connectivity issue for a species, plural, then we have to get that location right. And doing that effectively is largely unknown because we don't actually measure effectiveness of wildlife crossing structures very often, even though we're spending many millions of dollars to build them. So we have to get the first part right, which is decision support for where to put them. So there's been a variety of approaches that have been taken to saying, where should you put a wildlife crossing structure? I put a publication of mine first, just so it doesn't seem like I'm picking on other people. And I totally regret that first one. So intersection with linkages. Linkages don't really work as explanations for wildlife movement in general, but that's one way you can think about it. There have been a variety of other ways that wildlife crossing structures have been proposed for certain locations on the landscape and in general guidance. And there's also been combinations of those different approaches as well, which I think is the most common. So in this era of lots of new wildlife crossing structures, we really want to improve how we position them. Hopefully we want to improve how they position them. And this is a really good problem for geographic information systems. One of the primary driving forces for geographic information systems was locational problems in conservation. So it's an excellent tool to figure out how to do this, but GIS systems aren't black boxes, they're not magical, and so you're using them for decision support, not to make a decision, and you have to inform it with really good data. So the approach I'm using is built on a pretty tall literature basis, spatially explicit decision support, which is just what it sounds like. You're supporting spatial decisions, in this case with GIS. It's increasingly being used in conservation and other kinds of decision making, and it uses spatial data as the fuel and logic, different kinds of rules. We use logic rules as the operational rules to drive that machine. In this case, it's location of wildlife crossing structures. The examples I'm going to talk about are all funded by the Wildlife Conservation Board in California. It represents about $25 million in planning. Different locations around the state, lots of different stakeholders, and the output is to give a design, a 65% design, which is code for, you can then probably send it out to bid after that for 7 to 10 wildlife overcrossings in these locations. There's also a variety of other locations in the state that are using different methods, and so overall it's a fairly expensive proposition. Just for these locations, our implementation costs are likely to be in excess of $200 million. I'm not really positive what it's going to be. The next speaker is a good handle on costs and how we estimate that. Okay, so how do we do this? And the way to start, and it's true for any good prioritization or locational kind of project, is what's your objective? And this is sometimes opaque, should be transparent, and it often leads to wrangling. It's a polite way to talk about it. We call them wildlife crossing structures, but as Marcel correctly pointed out, we're often focused on certain ungulate species and not biodiversity in general. And so really keeping a tight hold on biodiversity as the objective probably is going to help them be truly wildlife crossing structures. We looked at both over and under crossing prioritization, used logic modeling to combine the data. We used equal weighting, but that basically means we're not unequally weighting certain data sets, but how you use those data sets may influence the outcome of the model, especially if you use more data associated with large species, which was some projects we did. And then finally, we developed different scenarios. And this last one is a way to compromise with those who cannot let go of megafauna as the goal for wildlife crossing structures. This is the simplified model for location prioritization. And you have to memorize all the boxes, but let's see if my cursor works. Not really. The ones on the top right represent large mammals and biodiversity. And the large mammals always showed up as a theme. So they got their own part of the puzzle. We always brought in other biodiversity as well. We brought in different kinds of land and traffic disturbance, ownership, and combined them using different logic approaches, and primarily this one at the bottom. And this is the AND operation, which basically says you have to meet all your criteria for a site to be good. So if any one of those criteria fail, like you've got a lot of adjacent development, there's just not a lot of wildlife there, or other things, then you get a low value automatically because of the AND relationship. So finding anything with an AND relationship is really a good spot. It's an optimal location. Used a wide variety of data, including collar data, camera trap data, crash data, that's carcass and crash as a reported incident with police, different kinds of wildlife occurrence data, habitat suitability models, which we're now validating, modeled noise and light, there's a talk about that on Thursday, distance to different land elements, topography for whether it should be an overcrossing or an undercrossing, and ownership just to make sure it's a feasible location, or it could be a feasible location. Okay, one thing we did for all of these is to rescale all of those data. They're all different units, distances, numbers, densities, etc. Rescale them to a common scale, which is a 0 to 1 scale. So what this is called often min-max or max normalization. So your largest value is usually 1 and your smallest value is usually 0. And then there's also invert max normalization, which means that you might do the opposite depending on what your variable was. We used linear functions, but it is possible to use nonlinear functions here as well. We also use home range functions for one of the projects. I'm going to go through a few of these, just showing examples of what some of the inputs and outputs look like. This is for US 395 in Glaston County mostly. And the boxes circled here are for collar data for mule deer and mountain lion, and for habitat suitability models. And so where the purple color is, here, indicates where those elements are at the highest density or rate. And then I've also put some roadkill data on top of wildlife vehicle collision data on top for large mammals, and you can see there's some correlation, but not absolutely. That's one type of data. Another type is to combine the large mammal, the all biodiversity data together. So the purple there, the darker the purple, the greater the value you're getting in terms of large mammals, movement, and biodiversity in general. The lighter the color, the less the value you're getting, or prioritization score. And then finally, this is looking at noise and light disturbance and adjacent development disturbance, saying if you have a lot of that, that's probably not a good spot for a wildlife crossing, either because of the barrier effect from traffic or because adjacent development may inhibit wildlife movement. And then you get what leads to a final prioritization, which is on the far right. But the way I've stepped to this is to take an individual highway. This is US 395. And so the first line here on the left, the first purple color line, is showing the distribution of large mammal and biodiversity priority scores across that highway. And then the next line, I'm adding disturbance. So we're incrementally adding some of these different variables to see what the effect is. So when we add disturbance, we narrow slightly those priority score locations. When we add land use, so ownership and development, we see an even greater narrowing to even fewer locations. And that's because we want to have conservation ownership surrounding the location. And so that means it's restricted to certain areas. And then the final line with the letters next to it is adding topography, saying if we want to build an overcrossing, you want a certain land form to optimize building an overcrossing. An undercrossing would have the opposite land form. Though engineers argue they can build bridges everywhere, anywhere. So in the East Bay, 3 different highways, Interstate 580, Interstate 680, incredibly busy highways. Surprisingly high rates of deer vehicle collisions on 680, which has some of the highest traffic in the East Bay area, still gets a lot of ridicule. And then Highway 84, all of these in the East Bay area, same kind of process. We look at adding biodiversity information together and disturbance from surrounding land use and traffic, land conservation, and topography until we get these final sets of location. I first started doing this kind of modeling a long time ago, and it is always incredibly lucky to have just a small set of locations. In other words, not 30 or 40, but just 10. I don't know why it's pleasing, but it just works out that way. Let's see. There was, in this case, as opposed to US 395, which had that large mammal emphasis, this was much more an emphasis on all species, all biodiversity. Okay, we also did a gaps analysis, which was saying, based on where different focal species were distributed, are there opportunities for them to cross the highway already? And compared those locations to the location prioritization that we just did. And so the red arrows indicate where there are gaps, which is the outside purple, and also priority locations where we use the modeling approach I was just showing. So those places are both good places to put crossing structures from a biodiversity point of view, but also places where we don't have existing structures. This similar process was carried out on State Route 152. I'm going to rip right through that. And then also on Interstate 8, focusing on one species, peninsular bighorn sheep. Okay, so final point, when we do all this, we're basically summing the ecological benefit of a potential crossing. And one interesting thing we can do, and Sasha Dansky, the next speaker, is going to go into this in more detail, is to compare that ecological benefit with the cost of building those crossings. So this is a benefit cost analysis or benefit cost ratio. And you basically want your benefit cost value to be greater than 1. You want the benefit to outweigh the cost. A requirement for doing that is you have to rescale all your benefits to the same scale, 0 to 1 scale, rescale your cost to a 0 to 1 scale as well. And so you're basically trying to find an optimal condition. And it's going to look something like this, where you have high costs, which are low score, low costs are high score. You can think about that. That's what you want. You want a lower cost. And then your benefit score on the y-axis here, you're looking for locations that give you that greater than 1 benefit cost analysis. Sorry, benefit cost ratio. Okay, finally, this is decision support. It's not making decisions based on a wide variety of data. And last point, I think it's amenable to statewide prioritization. We're going to try this next, is to take this approach and apply it to the whole state. And also do some sensitivity analysis to make sure it actually makes sense at those scales. Thank you.
We have time for some questions.
Just wondering if you had included any look at existing or proposed construction projects when analyzing your cost-benefit ratio.
It was more so post hoc after the fact, saying if there's already going to be something happening there, say Caltrans was going to build a crossing, which is true for the 395 location, even though it showed up as a high priority location, we wouldn't go further with it because it was already a plan. That's one way. Another way is to say, if they have a future transportation improvement project that could use mitigation, then that spot that we identified could go into that plan and add to that project in terms of new mitigation that maybe they weren't considering. And Caltrans, at least in some of these districts, are open to that kind of addition from this work.
Another question?
Super stuff. Was there a preference built in for crossings that would connect public lands, federal lands, over private lands, which have potential development threat?
Yeah, definitely. So, and that was sometimes brought in during the modeling to say, okay, we're going to deprioritize the locations that didn't have conservation ownership, and sometimes leave those in and then look at them after the fact and say, okay, if this actually is a good example. Let's see, right here, big parcels, all privately owned, surrounding a place that's a highest priority, biggest gap that we have, but surrounded by big private parcels. So we want to highlight it as maybe a place for conservation action, but it's unlikely to be a place we actually build a structure now or propose a structure now. It's just, if we could, that'd be the best spot to put it.
Another question? Getting my exercise today.
Just for your benefit cost analysis, how did you quantify the benefits? The cost is obviously pretty easy, but
I rushed through that. I misinterpreted the time cards. I was thinking I was completely out of time. So the benefit would be essentially these prioritization scores, which is the white to purple scale that's common to most of these maps, white being not so great, the purple being the best spots. And so those are already on a 0 to 1 scale. And so they provide us with the fuel for the benefits side of this equation. The cost would have to then be also rescaled. And you could use the lowest cost as one, a value of 1, and the highest cost is a value of 0, but I would say you probably want to use a non-zero value for the highest cost, just so you keep it on the range. But the ecological benefit is all from that prioritization modeling. And actually, I should say, it's not from the final one here, it's from the first one up here. But you can use different versions of this for the benefit. That includes aspects of disturbance and land use, et cetera.
We have time for one more question.
Up here.
Can you explain why these model results are not meant to be verified in the field?
It's my co-author. I did not know that question counts. So I'm trying to remember the answer to that. Because we just went through that. So these are based on, in turn, based on models to some degree, and other things that aren't models. And so there isn't really a test for them, which sounds unsatisfactory, but going out and standing at these spots and looking at them, which is as we know, a very typical activity, I would propose is a very useless activity, except for the social interaction part of it. I think that's the best part of it, right? I love field trips like that. Don, hero for the Wildlife Conservation Board, has come on a lot of those, and they are critical to getting these things planned and built, but they're not critical about where they should go. And so there really isn't a good way to do it a priori. After the fact, this is something every state should do, definitely California, is test all of these as they come out and say, did they work? Then you can go back and look at your initial modeling and say, okay, are we basing this on good assumptions, on good data? Should we be doing a better job? Should we be considering landscape considerations and breeding sites, as Marcel was pointing out? And that would be the way to test it. But a priori, this is not really a good way to test it.
Thank you, Fraser.
Thank you.